Welcome back to our series on mathematical statistics. I'm Mark Ledbetter. This is video 34, and we are in lecture 16, part B, and we are talking about confidence intervals for the differences of means, two means, mu1 minus mu2. Okay. So last time we looked at case 1 where n1 and n2 were both greater than 30. So in mathematics, the or means either or both, okay? It can be either or both. If n1 is less than 30 and or, the way we normally say it, or n2 is less than 30, that means that n1 is less than 30. If either n1 is less than 30 or n2 is less than 30 or both of them are less than 30, we have to use this one. If we have common variances, we don't know what they are. And you say, well, if you don't know what they are, how could you know if they are common? But there are tests for that, and we will actually talk about that in Chapter 8. So the assumptions for this, there are two of them. The populations have normal distributions. Why? Because n1 is less than 30 or n2 is less than 30. So the central limit theorem does not apply. CLT does not apply. So in order for this, we have to use that theorem about the linear combination of independent normal random variables. So the two populations have normal distributions and they are independent. The two populations have common variances, so sigma 1 squared equals sigma 2 squared. So our standardized form of x bar 1 minus x bar 2 simplifies to this. Remember, it was x bar 1 minus x bar 2 minus mu 1 minus mu 2 in parentheses divided by the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. Well, if both of them are sigma, then this portion is equal to, I can factor out sigma squared out of both of them. And then I take the square root. If I'm taking the square root of this, I take the square root of this. And this is equal to sigma square root of 1 over n1 plus 1 over n2. And thus we have our standardized form here. Now, the problem is we don't know sigma. So we can't just use S because just because sigma is statistically the same, that doesn't mean that S1 is equal to S2. Sigma 1 equal to sigma 2 does not imply that S1 is equal to, or it does not imply that S1 is equal to S2. Okay, does not imply that. In fact, it's since we're taking random samples that are independent, it's going to be almost impossible for S1 to equal S2 because they're different random samples. Okay, so we're going to use something called a pooled variance, pooled sample variance. And so what we do is we take n1 times s1 squared plus n1 minus 1 times s1 squared plus n2 minus 1 times s2 squared. So let me show you why we're doing that very briefly. Remember that we'll say s1 squared is equal to 1 over n1 minus 1 times the sum of x sub I minus x1. Okay, so we'll just leave off the subscripts. Remember that for s squared, this is 1 over n minus 1 sum of xi minus x bar quantity squared. So n minus 1 times s squared is equal to, I keep wanting to say n1, n minus 1 times 1 over n minus 1 sum of xi minus x bar squared. These cancel, so this is just equal to the sum of xi minus x bar squared. So we've got the sum of the squares here, and then the sum of the squares here, and we're adding those up, and then we need to divide by not n minus 1, but now we'd say we had n1 minus 1 in the calculation of s1 squared and n2 minus 1 in the calculation of s2 squared. So we shouldn't divide this by n1 plus n2 minus 1. We should divide it by n1 plus n2 minus 2. Okay? And so that's what we've done. We've added up the degrees of freedom and the denominators. It's the same thing, right? We've added those to get the denominator here. And this matches up. It's a logical extension of this formula, this formula for s squared. Okay? And if you recall, the expected value of s squared is equal to sigma squared with the n minus 1. Okay? So it's easy to show that the expected value of s sub p squared, this pooled variance, is equal to sigma squared. Okay? Which is equal to sigma 1 squared, which is equal to sigma 2 squared. All right? So the overall variance. 1 and 2, I didn't label them. Yes, I did. 1 and 2 here imply that W, which is equal to n1 plus n2 minus 2 times s sub p squared over sigma squared, has a chi-squared distribution. We proved this transformation last semester. Not exactly, but this is the degrees of freedom R. And so we showed that R times S squared, or and R in that case was n minus 1, divided times S squared divided by sigma squared had a chi-squared random chi-squared distribution with degrees of freedom n1 plus n2 minus 2. So whatever R is, chi-squared R. Sorry, got a little tongue-tied. So the t-statistic. Remember that the t-statistic is z divided by the square root of w divided by its degrees of freedom. W is a chi-squared random variable with r degrees of freedom. Z is a standard normal distribution. So I can substitute in for z. Here's my z that I came up with. And here is w. And this is r. And you can do the algebra, and it simplifies to this equation here, which is x1 bar minus x2 bar minus mu1 minus mu2 over s sub p, square root of 1 over n1 plus 1 over n2. And this has a t distribution with n1 plus n2 minus 2 degrees of freedom. Okay? Knowing that, we can choose a limit t sub naught such that the probability that this quantity is between negative t naught and positive t naught is 1 minus alpha, which is our C, or confidence level. By going through the algebra and isolating mu1 minus mu2 in the middle, we get the confidence interval, or confidence limits, x1 bar minus x2 bar plus or minus t naught times s sub p square root 1 over n1 plus 1 over n2. Let's do an example. So the systolic blood pressure again, but now I've called males 1 and females 2. Okay? So I just relabeled which one was which. So now I'm going to get a positive confidence interval instead of a negative one. And that's exactly what happens. From the last time, we had a confidence interval of negative 13.1 to negative 2.9. This was female minus male. So the confidence interval for male minus female would have been 2.9 to 13.1. We multiply both numbers by -1, and then when we do that, the order usually switches. So positive 2.9 is smaller than positive 13.1, but negative 13.1 is smaller than negative 2.9. So part A is we want to give an estimate of sigma squared. So the estimate of sigma squared is S sub p squared, which is n1 minus 1 s1 squared plus n2 minus 1 s2 squared over n1 plus n2 minus 2. And this is equal to, now let's see, so do they have the same sample sizes? We changed the sample sizes. So where's my data? I must be missing it. Okay. So I know that I relabeled it. Where is it? Oh yes, here it is. Okay, right there. So N1 is 15, N2 is 12. So I need N1 minus 1, which is 15 minus 1, times S1 squared, and we're given the square here, so we're going to use 193.21, plus N2 minus 1, 12 minus 1, times S2 squared, 146.41, over 15 plus 12 minus 2. I need to get rid of this so I have room to write. And this is going to be, so this is 14 times 193.21 plus 11 times 146.41 over, so this would be 25. So 15 and 12 is 27, minus 2 is 25. And this is going to equal 14 times 193.21 plus 11 times 146.41. That's going to be 4315.45 divided by 25, which is 172.618. Okay? And so we're not going to round this until we take the square root. This is the point estimate of sigma squared. Okay? And I could round it to one decimal place, 172.6. But make sure that you don't use this value. When you take the square root, take this value. Okay? So we want to give a 95% confidence interval for x bar 1, or for mu1 minus mu2. It's never about the sample, it's always about the population. So if I ever make that mistake, forgive me, but remember that it's wrong. Don't write a confidence interval for x bar 1 minus x bar 2. That's wrong, doesn't make any sense. It's for mu1 minus mu2. So we have, but the confidence interval is x bar 1 minus x bar 2 plus or minus t naught s sub p square root 1 over n1 plus 1 over n2. And x bar 1 is 125 minus 117 is x bar 2 plus or minus. Now I need t naught. Okay, so t naught, so t sub alpha over 2, and it's n1 plus n2 minus 2 degrees of freedom. Now we asked for a 95% confidence interval, so this is equal to t of 0.025 and 25. See, our degrees of freedom are right there. And this is equal to t-table 25 and 0.025. So I need 25, which is here. And I need 0.025, which is here. So that means that this is 2.060. That's my T naught. And then, so I have 2.060, and then I need the square root of 172.618. Again, don't round, even though we would give this as the answer for the point estimate, we'd round the answer. When you want S of P, you don't round until the end, so you don't round this. You use the exact value and then round the square after you've square rooted. Okay? And then we have 1 over, let's see, it's 15 plus 1 over 12. This is going to be 8 plus or minus, and I want this number. And I want it rounded to 1 decimal place because my data is blood pressure, and that's to 0 decimal places. So I want 1 more decimal place for the scientific method times. This is the square root of 172.618. So I don't ever write out the value of this because I need all the decimal places. I can't round. And I don't write out the value of this either because, again, I can't round it. I just need to do it all in my calculator at once. So 2.062 times the square root of 172.618 times the square root of 1 over 15, or 15 to the negative 1, plus 12 to the negative 1. And that gives me 10.48228. So we can round this to 8 plus or minus 10.5. Round it to 1 decimal place. And this gives us 8 minus 10.5 and 8 plus 10.5. And this is negative 2.5 to 18.5. And notice that 0 is in the interval. And let's look at the previous one. For N1 equals N2 equals 50, we had now we had negatives, but it's going to be 2.9 to was it 2.9? Yeah, 2.9 to 13.1. And this is again for females minus males. Now we did males minus females, so we had the negative of this. So 0 is not in the interval here. So with N1 equals 15 and N2 equals 12, and basically, if we came up with the exact same mean, sample means and sample variances, then with n equal to 50 for both, we find that they are different, that the male and female blood pressures are different. But when we are using this very small sample size, and they're not even equal sample sizes, then we get a different result with the same x bars and the same s squares. We find that there is no difference between these. So the sample size is very important. It says, besides a common variance, what other assumptions must be met? And that is that we have independent, the two populations are independent of each other and normally distributed. Because in this case, both sample sizes are less than 30, but if either one is less than 30, then both have to have normal distributions in order for us to be able to use this method. So what I didn't do here, I forgot to write, was our interpretation. So we are 95% confident that the interval negative 2.5 to 18.5 contains the true mean difference it was systolic blood pressure, so I'll say systolic blood pressure between males and females, and you might want to say males minus females, using random samples N1 equals 15 males and N2 equals 12 females. Oops. Females. There. Sorry, all right, so we are 95% confident that the interval contains the true mean difference in systolic blood pressure between males and females, males minus females, using random samples. N1 equals 15 males and N2 equals 12 females. All right, that's it for this video. I hope you've enjoyed it. If you have questions, then please come to virtual office hours, and I'll be glad to try to point you in the right direction. If you need help before you can make it to virtual office hours, then by all means email me, and I'll do my best to help you through email, and I'll respond to you as soon as it's possible. Please take care of yourself so we can see you next time.